Hi there, welcome back to the channel, and in today's video we will just be complementing last week's video covering Kirchhoff's voltage law by now covering Kirchhoff's current law. So I'll just be starting by going through an explanation of the equivalent formula for Kirchhoff's current law and how to interpret that by means of a circuit, and we'll put this to the test and verify Kirchhoff's current law by solving some circuit problems. So let's start by discussing Kirchhoff's current law statement. Kirchhoff's current law states that the current flowing into a node or a junction, which we can write as the summation of the absolute value of the input current, must be equal to the current flowing out of it, which we can write as the summation of the absolute value of the output current. Now, what do I mean by absolute value, for those of you who don't know? What absolute does is takes any negative value and turns it into a positive value, and I can show you a sine wave to represent this. So this is a typical sine wave here, and if I was to take the absolute value of this sine wave, this is what it would look like. See, it takes any negative part and turns it into a positive part. So now we've covered that, let's try to interpret this formula, for a circuit, because that's what we want to do, right? So let's start by drawing one. Here we go. This is R1, R2, R3, and this is V1 voltage source. And this is also node A. So we have this current that flows out from the voltage source through this resistor, which decreases the voltage as it reaches this node. And at this point, the current flowing into this node must be equal to the current that flows out this way and out this way. I3, I2, and this is I1. So it can be said, therefore, that I1 equals I2 plus I3. And rearranged, I1 minus I2 minus I3 equals 0. And that's how you verify KCL for a circuit. So now I've covered that basics, I think we're ready to solve some problems. Okay, let's start with problem number 1. What I want you to do is verify KCL for this circuit. Take your time if you need to and pause the video to work on the solution. To start by solving this problem, let's find the equivalent resistance. So, since we have just two parallel resistors, we can use product over sum. 1 times 2 over 1 plus 2, which will give you a value of 2 over 3 kilo ohms. Now take note, this is different from what we've been dealing with in previous videos. What kilo means is times 10 to the power of 3. So now we found the equivalent resistance. Let's find the equivalent current flowing through this circuit. So 12 divided by 2 over 3 times 10 to the 3 will give you 18 milliamps. Again, take note, the small m means milli, and that means times 10 to the minus 3. And that's your total current. So now we found the total current flowing through the circuit. We can start by verifying KCL by finding the current that flows across R1 and R2. So let's start with R1. Use Ohm's law, 12 divided by 1 times 10 to the 3 will give you 12 milliamps. Likewise for I2, 12 divided by 2 times 10 to the 3 will give you 6 milliamps. So let's take a closer look at the circuit. 18 milliamps flows into this node and 6 milliamps will flow that way. 12 milliamps will flow that way. Therefore, this verifies KCL for the circuit and the problem is complete. Same style of problem once again. What I want you to do for this circuit is to verify Kirchhoff's current law. Take your time if you need to and pause the video to work on the solution. Okay, the first step would be to find the equivalent resistance. So this time R1 is in series, but however R2 and R3 are in parallel. So 1 plus 3 times 6 over 3 plus 6, so that's the same as 18 over 9, which is equal to 2. So our answer is 3 kilo ohms. That's our total resistance. So now we have the total resistance. We can find the total current flowing through the circuit. So 9 volts over 3 kilo ohms will give you 3 milliamps. That's the total current. So now we've found the total current. Let's find the voltage drop across R1 because it's in series with the power source. So voltage drop across R1 is 3 milliamps times 1 kilo ohm, which will give you 3 volt drop. So because 3 volts is dropped here across R1, 6 volts will make it to node A. So this is important because when we find the current that flows across R2 and R3, you will see that it sums up to 3 milliamps when we account for the voltage drop, I should say. So 6 over 3 kilo ohms will give you 2 milliamps. And for R3, 6 over 6 kilo ohms will give you 1 milliamp, which is correct because 3 milliamps minus 2 milliamps minus 1 milliamp equals 0. That verifies KCL for this circuit. So thank you very much for watching. I hope you enjoyed the video and learned something new about Kirchhoff's current law. And next week I will be introducing you to complex numbers and why we use them in electrical engineering.